Okay, today. Move that out of the way. Using the difference quotient to find instantaneous rate of change. If you're right with me, you're frowning going, isn't this the exact same as yesterday? Yesterday was tangent slope, today's instantaneous rate of change. Aren't those two things the same thing? And the answer is, they'll give the same value. They are different things, really. Tangent slope is on a graph. It's a slope. Instantaneous rate of change is how much is something changing right at a particular moment. But yes, they give the same answer. They're the same number all the time, but they have a slightly different interpretation is all. You go, okay, that's fine, but isn't it going to be the exact same mathematics? And the answer is absolutely. This is just a second version of yesterday's note to go, okay, did you sort of get it the first time? Yeah, I sort of got it the first time, and now I'll do it all again to make sure it's very clear what we're doing. I got news for you. One of the lessons of the next chapter is the exact same lesson again. That's how important this is. And we'll change its name one more time, and we'll call it the derivative. Yeah, so those of you who heard that word, that's what's coming, is the derivative. And we're essentially doing that already. So here we go. Using the difference quotient to find instantaneous rate of change. Warm up. Complete on a separate page. Okay, I'm ready. Determine all the points on the curve f at x equals 5x squared minus 7x plus 9, at which the tangent slope is 28. Now, I'm going to act like I don't realize that this has to be done with a values. I'm not going to think it through. I'm going to use this example to show why a value is so important. Okay, because actually there's no other way to do this. I don't have a number to use. So I'm going to use a values, and then when I get to the end, I'm going to go, oh, that's why the a value thing's so important. Here we go. To find the instantaneous slope of the tangent. No, that's not saying that yet. Okay, so back here. Hang on. To find m tangent. What we're going to do is we're going to go limit as h approaches 0 of f at a plus h minus f at a over h. I put that on your memorization board at the back of the class there after you left. I did two of them, actually. I did m secant without the limit. I did m tangent with the limit. It's an important idea. Not difficult, I don't think, but it's an important idea. And let me draw the picture up here of what's going on. There's a point they want to find the tangent at. I'm going to draw so there's some point that they want the tangent at, and that point is a comma f at a. And f at a makes things look like they're complicated, but it's not. It's just telling you to get the y value, sub your a into the function. Then move to the right a little bit. Yeah, and go just a little bit over. That a plus a little tiny bit, a plus h. H is going to represent that 0.01, 0.001. We want h to head to 0 eventually. Somewhere in this question, we're going to send h towards 0 from both sides. It's a limit, right? So it goes from both sides. It's good. All right. And then the y value of that second point is f at a plus h. That looks complicated, but it's not. It's just saying, once you know your a plus h, sub it into the function to get the y value that goes with it. Okay? And then so, when we want to find the slope of the tangent, what we want to do is go y2 minus y1, f at a plus h minus f at a. That's the numerator. And then the denominator is a plus h minus a, and our cancellation already starts to happen. We learned yesterday that we want some cancellation to happen here, and the a's here cancel immediately, and I've just got h over there, making the difference quotient. Fancy name for an idea that we've been working on for a while. Now, that would get the slope of a secant. And our job is to keep moving closer and closer. You've seen this diagram hopefully a million times now. Closer and closer, and this thing, as h approaches 0, as I get really close here, these secant slopes will head towards the slope of the tangent. That is, the limiting value of the secants is what the slope of the tangent is. Okay, that's explaining that's this, yeah? All that right there. Here I go. Limit as h approaches 0. I'm going to do with a's because I've been arguing that's the more powerful way to do it. And this example is going to show off why it's so powerful. So a plus h into the function. 5 bracket a plus h squared minus 7 bracket a plus h plus 9. And I'm going to stop right there because people who had trouble with this, there were 4 or 5 people who asked me about this yesterday. It had to do with what did you just do there versus what did I do over here. So I'm going to switch colors here. Minus 5a squared minus 7a plus 9. See? This one over here in red is a plus h. I just took a plus h and subbed it into the function everywhere I saw x. That was my x value. A plus h is what I was subbing in. A complicated x value. And now you see maybe why we had to wait to grade 12 to do calculus. Subbing into functions is difficult. Subbing a plus h into functions is really difficult conceptually. But once you get the feel for it, you're like, oh, I'm just putting a plus h in wherever I see x. And then f at a over here, I'm going to write over that in blue. F at a. And when I did that over here, I went subtract, and then I subbed a into the function. And at that moment, you sort of get disheartened by how much algebra you have to do, unless you've done a lot of practice. If you did a lot of practice last night, you're like, okay, yeah, no problem. Multiply out the brackets, collect the like terms, it's going to be a big mess. And then some magic's going to occur. Yeah, some awesome calculus magic coming up here. Me personally, I don't like mistakes, and not because I'm a perfectionist. Well, I don't like mistakes because obviously it's my job to not make mistakes on these. But I also don't like mistakes because I know how much work I have to redo. So I'm sort of a slow and steady person. I just do one step at a time. I don't try and rush this whole thing because I don't want to make a mistake. So I leisurely make a plus h squared into a plus h times a plus h. I'm going to distribute that bracket. Going to distribute that negative there. I already feel like I've made a mistake, so I'm going to recheck it to make sure I don't have a mistake carrying through here. 5a plus h, yeah. 7a, 7h, yeah, 9 minus 5a squared plus 7a minus 9. Yeah, everything's good. I was worried for no reason. And then I'm going to distribute out those brackets. Me personally, I leave the coefficient out there. I do the distribution that's inside first, and then I use the coefficient at the end. That's how I handle it, but you can do it what you want here. I get a squared plus ah plus h squared. Oh, you're going to do that 1,000 times. You know, if you do a bunch of these, you're going to be like, okay, I'm at the point now when I see a plus h, I know exactly what's coming. And maybe you're so good that you shortcut this thing a little bit. That's great. Maybe you don't write out the a plus h times a plus h because you're just that darn good now. You know. When I do them on the board, though, I'm going to show every single little step here. And negative 7a, negative 7h plus 9 minus 5a squared plus 7a plus minus 9. If you're right with me, you're like, couldn't you start tidying up all that stuff on the right-hand side? Yeah, you really could. And as you're doing your homework, you can start tidying these things up as you go and save yourself some writing. In the interest of drama and showing off how awesome this derivative, this tangent slope, this difference quotient thing is, I'm going to leave it all out there and have my dramatic moment in a minute. I hope you know what the dramatic moment that's coming is. One more line before I get my drama. Limit as h approaches 0, 5a squared plus 5ah plus 5ah plus 5h squared minus 7a minus 7h plus 9, careful, minus 5a squared plus 7a minus 9. Those of you who are messy writers, you're probably going to start improving now because you just won't be able to afford any mistakes. So you're going to start writing neater just because. And if you have little tricks you do as far as writing little diagonal fraction things and so on, you're going to start getting rid of those too because you just won't be able to afford any little mistakes here. Yeah. Okay, here comes the drama. And I'll act like I don't know what's coming just so you really impress on you the amazing part that's come here. You go, okay, well, I see a 5a squared there. 5a squared, I'm looking for other a squareds, 5a squared minus 5a squared. Oh, those are a terms, and they just happen to cancel. 5a squared minus 5a squared. Oh, that was good. 5ah. 5ah, another 5ah, any other ah terms? No, so I get 10ah. If you have trouble keeping track of these things as you go, then maybe you're getting some kind of highlighter, or maybe you got your own little trick to make sure you cross off the terms that you're done with. You know, maybe you underline them. Maybe you put check marks on top of them. There's all sorts of great algebraic techniques to keep track of what's going on out there. Then, next term, 5h squared. Any other h squared terms? No other h squared terms. So that's 5h squared. Oh, maybe I'm going to blow a little check mark above that one to say, yep, took care of that one. Let's see, negative 7a. Any other a terms? Positive 7a. Huh, look at that. The a terms went again. How convenient. I wonder if that happens all the time. If you're right with me, you're like, it has to happen. If this is going to work, it has to happen. All those a terms have got to go. Then I get negative 7h. It doesn't have a canceling friend, so I get a negative 7h. And then I get a plus 9 and a minus 9. This is when you start feeling real good that you've done the algebra right. Plus 9, minus 9, those have to go. And what I get is this nice little thing here. And all the terms that don't have h in them cancel it out. Why is that so incredibly important? Why was Isaac Newton just jumping up and down all around his house when he realized this was going to happen? So the h's can go. So I can do this limit. It must be able to be done. This limit must be able to be done. There must be a tangent slope. He said lying. There doesn't have to be a tangent slope. But these nice ones that we're doing with a nice x squared graph, of course, it's going to have a tangent slope everywhere. Is there functions that might not have a tangent slope? Yeah, if you had a corner or something there, maybe there's not a tangent slope there. Don't freak out. I'm not setting you up for disaster on the test, because there was a question in the homework like this. But next chapter, we got to get to the bottom of this and talk about, is there always a tangent slope? And so that's what I'll teach tomorrow before your test. So you can see that stuff, but it shouldn't mess you up. Anyways, I'm going to do what Heather suggested there. Is I'm going to common factor out the h. You actually don't have to when they're nice and simple like this. You could just divide h into each one of these. That's a nice shortcut too. But I'm going to do the common factoring because there are questions where the common factoring is going to really help you. And that all is over h. And so then my h's cancel, which is exactly what we hope for. The 0 over 0 part of it canceled. What that means is, yes, you still can't sub in h equals 0. That is, I cannot find the value of this function at h equals 0. I can't get a slope of a secant. But that's not what this question's asking. It's saying find the limit. And we found out with limits, even though there's a hole there, we can still find out what it's heading towards. And that's all we were asking at the start anyways. What is this thing heading towards? I've run out of space down here, so I'm going to move over here. Therefore, oh, I don't want orange. Orange is my fancy cancel color. Red. Therefore, m tangent equals limit as h approaches 0 of 10a plus 5h minus 7. Now I can sub in the h equals 0. Let me just get distracted for a minute. You need these limits all the way down. You're like, do I have to write the limit every line? Yeah, you really do, because it's reminding you that at some point I got to sub in h equals 0. So it's an important piece of it is to have that limit out there every time. Now I sub in the h and I get, something's wrong. Got so distracted with my limit lecture I forgot to write the a. There. 10a plus 5h minus 7. And when I sub in h equals 0, I get 10a minus 7. And yesterday, when you got down to that line, if you didn't do it with a's, you would have got the answer. M tangent equals 4 or 11, negative 2, 1/2, whatever it is. I didn't do that here because I'm trying to convince you that doing it with a's is a little more difficult, but infinitely more powerful. That is, if this question asked, find the slope of the tangent when a equals 2, I could just sub in a equals 2 now. And then if they turn around and said, well, check when it's a equals 9. I go, no problem, a equals 9. I don't have to go through the whole process again because I've got an equation that relates slope of the tangent to whatever a value you want to talk about. Question?
So you do the limit for 0 and then the a value is just the value where it wants you to find it at?
Yeah, he says it perfectly. The h is sort of a dummy variable in all this. The h eventually goes to 0. I won't say it doesn't matter. It really matters, but it's not like an essential part of the question in a sense. The essential part of the question is the a value, the a that we're going to use here. And if this was like last night's homework and they said, okay, now find out when the slope of the tangent is, or what the slope of the tangent is at x equals 2, then you just make your a value 2, because for this question, the a value happens to be 2. Now to really show off the a value. This question doesn't say that. Let's just imagine you come test time and you do this all procedure and you go, I'm going to use the a's because Mr. Todd is very wise, and so I'll use a's. And you get down to here and you go, okay, now let's read the question and find out what a value I'm going to use. Determine all the points in the curve at which the slope is 28. They don't give you the a value. They give you the slope. And because you did it with a values, you're like, yeah, that's no problem. I don't care whether you give me the a value or you give me the slope. Now I can find, think about this power for a second. Now on the graph of 5x squared minus 7x plus 9, some crazy parabola, we can find out where the slope is 28. Yeah? Very, very big power difference in using the a value. So we want m tangent equal 28. So I go 28 equals 10a minus 7. Move the 7 over, I get 35. Oh, this is in the way. Excuse me, move up there, please. I get 35 equals 10a. 35 over 10 equals a. A equals 7 over 2. An x value of 7 over 2 will do the job here and get me slope of 28. Now the question might have confused you. I want to fix something in the question. I'm very careful on tests when I phrase stuff like this. It says determine all the points. It says points. That would scare you in this question because like it says points, you know, and I would put a bracket around the s. Lots of times you see that in math tests. Points. It's like saying, I don't know what you're going to find here. Maybe you'll find one, maybe you'll find lots. Don't freak out. Whatever you find is right, hopefully, if you've done all the math right. And here it was just 1 point. Ooh, I didn't have the point. A equals 7 halves. I got the x value. That's not the point. Yeah, this is what I was talking about yesterday. As you're walking up to hand your test, and you're like, did I answer the question? Because it's easy to get caught up in all the algebra and go, I did it. I landed it. 7 halves. It's good. Then reread the question. What's the point? Oh, what is the point, Mr. Todd? Okay. I ran out of space. Let me just build a new page in here. Insert page, blank page, before current. Oh, not before current, after current. Silly Mr. Todd. I'll just move this up there like that. Move this down there like that. Okay, now I'm ready to go. Back to here. On to my next page, and I forget, it says, when a equals 7 halves, how do I get the y value now? You just subbed in. Okay, we've been hammering away on this idea that all of these things are just saying sub in, sub in, sub in. So now I'm subbing in. And having a sub for lunch maybe now that I'm starting to think about it. F at 7 halves equals, and I completely forget the equation, so I'll have to go back and forth here. What was it? 5 times 7 halves squared minus 7 times 7 halves plus 9. 49 quarters minus 49 halves plus 9. 245 quarters minus 98 quarters plus 36 quarters equals, oh, can I do it in my head? 147, 181 over 4. I don't know. I gotta check it. Get my calculator out and check it. We'll see if Mr. Todd's getting old here. 45.25. Okay. 5 bracket 7 divided by 2 squared minus 7 bracket 7 divided by 2 plus 9. No, it's wrong. I made a mistake. 49 halves, which is 98 quarters. 9, okay, quarters. 245 quarters, yeah. 98 quarters, yes, that's right. 36 quarters. Maybe my addition is wrong. 245 minus 98 plus 36. 183. Oh, no. Don't tell Mrs. Todd that happened, okay? How did that happen? 194 is 247. Oh, yes. 147, 183. Oh, anyways, I don't need that down there. 183 quarters is good. Therefore, the point is 7/2, 183 quarters. Can't I just use decimals? Well, sure, you could. I mean, if you want to round things off and work at Samsung your whole life, I guess that's okay. But if you want to work at Apple or somewhere good, then you got to do, you got to get it exact. You can't play around and have pink lines in your screen and phones that blow up and stuff like that. That's no good. Yeah. I don't know. I don't see too many Samsung phones around. Is that a funny joke anymore? Are we all Apple now? Samsung. Oh, there's Derek over there going, okay, that's fine. I'm going to do a decimals. Yeah, okay. Any questions there? Can you believe the cosmic power we have all of a sudden? We can find out a point somewhere on this graph that has the exact slope we want. And actually, the fact that the slope was a nice number is irrelevant to us. They said tangent slope 28. If they want a tangent slope 47.24, that's no problem. We can handle that in the middle of all this too. That's not a big issue. Do you see the power of the A value? Yeah? Start switching over as soon as you can. You're like, okay, I'm still having trouble with these. I'm still using the number because it's easier for me to do the algebra. Fine. Once you get used to the algebra with a number, then switch over and use the A value. What was the next one? Geez, toy rocket and small. Okay, I can't read that. Okay, so here's the actual lesson. That's really yesterday's stuff. Today, use the difference quotient to find instantaneous rate of change. Since we know how to use the difference quotient to determine slope of the tangent, we can also apply it to real-world situations involving instantaneous rate of change. Well, that's a perfect almost description about what's going on here. Slope of the tangent is what it would be on the graph. Instantaneous rate of change is what we'd be talking about sort of if this was a real life problem somewhere. So it says a toy rocket is launched straight up, so its height s in meters at time t is given by s at t equals negative 5t squared plus 30t plus 2. What is the velocity of the rocket 4 seconds after it's launched? I know what I've been saying about A values, but just in case you're not there, I'm going to go back and do this one. They gave me the number. I don't need to do it with A values. And if you get really good at these, you're like, I'm only going to use the A value when I have to, and I don't have to here because they gave me the 4 here. So I'm ready to rock and roll with a 4, and I'll do the algebra with 4. And I'll come back, and I'll do a different one with A values.
So 4 is our A, and we're trying to find the tangent at A equals 4.
Right, perfect. We're trying to find the slope of the tangent at A equals 4, but in this question, it'll be called instantaneous rate of change. Well, it won't even be called that. It'll be called instantaneous velocity for you physics people, yes? But they have a fancy word for instantaneous rate of change. Not all disciplines do. Okay, so I'm after instantaneous rate of change, which very soon we'll just start calling that IROC. Yeah, I remember doing that, calling it IROC last year. No one wants to write out instantaneous rate of change every time. And you physics people are like, aren't we just talking about velocity here? I'm like, I'm going to write that in the next line to make sure it's clear. We're really just talking about instantaneous velocity here. So we want limit as h approaches 0 of, I know, it's f at a plus h, but the function here is s, so I better start thinking about that in a second. But, okay, let me just write down the f first. F at a plus h minus f at a all over h. If you're still having trouble understanding this, I tried really hard in the first example to explain carefully where this comes from. So you can rewind the video. Or you can go back and check that explanation out again so you understand exactly where the difference quotient comes from and why there's limit as h approaches 0 out there.
Is ST really a problem? Because it'd be the same as f of x, right? Divide seconds by subbing in.
Yeah, I've done it before where I just go, I'm a little confused by the letters you've used. So I just write beside this, I write f at x equals negative 5x squared plus 30x plus 2. And I'm like, hold on, let me just do it with the variables that I'm used to. But I'm going to try and do this question as they asked, with s's and t's, okay? So I need a slightly different version of this. I hope it's not that weird. Instantaneous velocity will be limit as h approaches 0 of s at t plus h minus s at t over h. And I'll do one step better to really try and improve our symbology here. What I'm really after is the velocity at time 4. That's what I'm really trying to accomplish here. And to do velocity at time 4, I'm going to do limit as h approaches 0 of s at 4 plus h minus s at 4 over h. If what I'm doing there confused you at all, just give it a little time. You know, it's not as bad as it looks. I'm just trying to write it in the right symbols for what this question asked. But the question was right. You could just switch this to f at x right now and just do it as an f at x question, and at the end say, okay, what I'm talking about here is instantaneous velocity. But this handles it nicer. I like this setup better. So v at 4 equals limit as h approaches 0. Do you have to write limit as h approaches? I know it's a pain. Do you have to write this every time? Yeah, why? If I don't write that, what am I talking about? I'm talking about secant, not tangent. This is what makes it the tangent. That's the difference there. And that's why I wrote both on the board back there. So you can stare at it and go, okay, the difference quotient is about secants. The limit as h approaches 0 turns it into tangents. Question? Better? Yeah, good. John's question was, Mr. Todd, can you write neater, please? Now I don't know if I got enough space here. You know, everything that's happened here, I should have kept that line over there. And, oh, can I fix it? Sometimes it lets me fix it. Here, let me just play around here a little bit just because I like playing with my active board sometimes. Nope, it's all tied together. Look at that. It won't let me grab that line. Anyways, hopefully I've got enough space here. Oh, maybe I can just grab that whole thing, can I? Oh, yeah, baby. Woo! S at 4 plus h. Negative 5 times 4 plus h squared plus 30. 4 plus h plus 2. I'm going to write that all in red. Then I'm going to write the second part in blue, if it's a little confusing what I'm up to there. That was when I subbed in 4 plus h. Now I'm going to write subtract, and then just s at 4, which is negative 5 times 4 squared plus 30 times 4 plus 2. Oh, it fit. Oh, that's nice. And I'll keep going, and you just accumulate your questions as I go along here. Because if you did a bunch, or even some of this homework, you're like, oh, well, I'm home free now. You know, this algebra is not necessarily my favorite thing, but the rest of it's all pretty straightforward algebraic stuff. So I'll just cruise along, and you just interrupt me with questions as soon as I do something you don't like or make a mistake. Hopefully I don't make one here. Okay, so negative 5, 4 plus h times 4 plus h plus 120 plus 30h plus 2, subtract. Okay, I'm going to do that whole set of brackets as 1. That was a 4 there. Oh, try it in your head first. Negative 80 plus 120. Negative 80 plus 120 is 40, and then I get 42. That's my, I'm going to check my calculator, but I'm trying to stay young there, okay? Negative 5 times 4 squared plus 30 times 4 plus 2. 42. Still got it. Yes. Now some multiplying out some brackets. This very repetitive binomial distribution. It's like, seems like it's in every question of these, yes? Negative 5, let's see, 16 plus 4h plus 4h plus h squared. I'm going to keep everything else for drama's sake here because I'm still trying to show off how awesome this derivative, this difference quotient is over h. One more line before the drama hits, and I'll pause for questions there. Negative 80 minus 20h minus 20h minus 5h squared plus 120 plus 30h plus 2 minus 42. Can you do better and shorten this down? I'm sure you can. If you can't, and you're like, no, I need to show all the steps. Wonderful. I like that too. Show all the steps. Oh, all this stuff's in my way now. Can I fit that up there? And I'll just drop this over there. It's good. Oh, I promised to pause for questions there. I'm going to pause for questions and just stare at that for a second to make sure I'm very happy with it. Yeah, it's so good. Let's see. I'm 48 now. The first time I saw this, I was probably 17. 31 years, and I'm still thrilled by what happens here. But I pause for questions. Do you have any questions on those 4 lines of algebra? With any new algebraic technique, it's like that. The first time you see it, you're looking at the teacher going, are you out of your mind? I can't do all that algebra. Then I do it 3 or 4 times. Then you do it 3 or 4 times in your homework, and you go, okay, well, I guess that wasn't so bad. Of course it's not. Less smart people than you have got through this. Of course it wasn't that bad. Okay, here's the drama one more time. After this, I promise to behave and not be dramatic about these things. Let's see. Negative 80 plus 120 is 40. Plus 2 is 42. Minus 42 is 0. Wow. This one worked out nice, didn't it? Those numbers had to go. They didn't have h in them. They had to go. And it makes you feel good when you're doing the algebra that's like, oh, it's working. It's happening. And I'll show that cancellation again. Or I think I'm a check mark person. I just check them off like this as I've dealt with them. Those all went. Ooh, that one didn't go. What am I talking about there? That didn't go. Careful now. Negative 80, 120. 2, this one went. There's the one that went. Okay, those are all gone. And then I just collect up the other ones. You'll get super fast at this as you're going along. How many h's? Negative 20, negative 40, and another 30 over here. Negative 10h. Negative 10h minus 5h squared. All over h. You can just cancel the h's at that point. I'm just going to keep doing common factoring because there are some questions where the common factoring is the only way to see what's happening. So I'll stick with that. Common factor out the h, negative 10 minus 5h. Maybe you common factored out negative h. Yeah, that's fine. That'll work out too. And now the h's cancel. And then my question, maybe you already know what the question is going to be. The question is going to be, why is that cancellation so important? Now we're not dividing by 0 anymore. This is a hole in the domain. H can't be 0. But in the limit, I can find out what it's heading towards. Yes, it's a hole, but I can still find that limit, which is all I wanted in the first place. Where is it headed towards? And now I can finally drop the limit. Negative 10 minus 5 times 0. That's the moment that you're allowed to get rid of that limit as h approaches 0 part. And I get the answer equal to negative 10. Negative 10? You physics people aren't fazed by that, but will you non-physics people, how can this velocity be negative 10? What's the rocket doing at that time? It's on its way down now, yeah? And all this complete the square to find the vertex stuff seems a lot less important now. It's like, wait a minute, I can just find the slope anytime I want. Bang, bang, done. Well, bang, bang, done. It's just like this, See, like now you're looking back going, I guess complete the square wasn't that bad at the time, comparatively speaking. The difference here, though, is I don't care what the function is. You can line up any function you want, and I can do this and make this happen. I'm lying a little bit. There's some functions we haven't dealt with yet, but we'll get to that. Next chapter, I'll start talking about, okay, so which functions can we do this with? Which functions can't we do it with yet? And then we'll fix that. Therefore, the velocity at 4 seconds is negative 10 seconds. Did it say meters? Yes, meters per second. Or you could say the velocity at 4 seconds is it's going down at 10 meters per second. If you said the instantaneous rate of change at t equals 4 is negative 10, yeah, I'd do one of those unhappy dances as I was marking. I'm like, yeah, well, that's true, but that's not really what the question asked, So, and if you said the If you used F's and X's here, I'd be like, we'd like to get to the point where we can deal with whatever variables are thrown at us so that we can help all our friends in chemistry and physics do their math homework. Yeah? Okay. Do you have questions there? Oh, more time? I didn't see anyone's pencil moving, so I assumed that we were good for time. Oh, square root, thank goodness. I hope one of the lessons you've learned about square roots is there's a really important trick we need to know, but this isn't going to take 2.5 pages anymore, as long as you know the really important trick, right? Yeah, the conjugate. You already know what's coming. Good. That's helpful now when you look back on those limit things we were doing. You're like, wait a minute. When I see the square root, I know what to do now. I didn't have to memorize that list quite as bad as I thought. I know the square root one. That's conjugate. I might have to memorize the other pieces. Well, hopefully you know factoring too. Now it's getting a little easier to memorize that list of techniques because a couple of them have been picked off there. Okay, here we go. The total cost in dollars of manufacturing X calculators is given by C at X equals 10 root X plus 1,000. Determine the rate of change of cost when 100 calculators are being manufactured. They're asking for instantaneous rate of change because they've only given you one value of 100. So find the instantaneous rate of change at 100. Okay? So this is what comes up in your mind as you write down M tangent equals limit as h approaches 0, f at a plus h minus f at a all over h. And again, at the start of this lesson, I was very careful to do a full explanation one more time about where this all comes from. So if as you're doing the homework tonight, you're like, do I get this thing? Do I understand where it's coming from? I mean, I can use it, but do I understand it? Then you can go back to the start of that video and watch that carefully again.
They give us X as a variable here, so do we just use A and H as our default then?
A is a specific X value.
Okay.
So yeah, this is really in X's right now, but maybe I should do better. Instantaneous rate of change, totally allowed that short form the rest of the way. Any math, physics, chemistry people know IROC. We all talk about IROC. And so this is now limit as h approaches 0. That doesn't change, but maybe I should be using C at a plus h minus C at a over h. And in the interest of going back and forth here, I'm going to go back to A's this time, because I'm going to show off the power of the A's here again. And they gave me a specific A of 100. Yes, I know later on A is 100, but I want to show off that you can do this with the A's, not bad, okay? So C at A plus H, I'm taking A plus H and subbing it into the function. So I get 10 root A plus H plus 1,000. And then I got to subtract in brackets. Oh, I'm going to put it in blue. C at A is 10 root A plus 1,000 all over H. So I subbed A plus H into the function. You can hear my voice slowing down there as I'm like, let's just be careful here with our subbing. 10 root A plus H plus 1,000 is what I got when I subbed in A plus H. Then I subtracted, I subbed in A into there. And again, if you get to any of these homework questions and you're given the A value, you're like, oh, the A's messed me up, then just do it with 100. It's a little bit easier with 100. But when you can, try to use the A to get yourself ready for tougher questions. Question?
I see that we're going to have the 1,000s cancel out. Can we get rid of those before we multiply by the conjugate, or do we have to keep them in?
He asked a great question. What order should I do all this in? And let me just show you that off here, okay? Or show that off here. Limit as h approaches 0. Look at this. I didn't even do it on purpose. See, I'm indenting with the equal sign because I know with radicals, there's going to be space, Not like the polynomials where it's like, I don't know how much space I'm going to need here. You got your regular paper there or whatever, so you can just scroll right along. But I mean, I'm aware of these things. Okay, I'm just going to go slow and careful and try and answer Luke's question in the process. All I did was distribute that negative in the second brackets, and then the cancellation that you saw and predicted was going to be there. And that's great that we're at the point where it's like, I'm looking for these things to cancel, and they do go nicely here. Much easier than the previous question that those went. And your question was, can I get rid of those before I do the conjugate? And I say, not only could you, you should. You should do all you can to this thing before you do the conjugate. In fact, I'm going to convince you that there's something else I can do to make my life a lot easier before doing the conjugate. And this is going to take some real foresight by someone, or some real seeing through the question, or really finally all my harassing in advanced functions about a certain move comes to fruition finally. What else could I do before doing the conjugate thing? Common factor of the 10. That's why common factoring is a big deal for all sorts of reasons. But to make your life easier is the most important one. In fact, that common factor of 10 can go all the way out here. How nice is that? And if I did too much too fast, let me know right away. I common factor the 10 out of both of those numerator terms. And not only that, because limits are friendly, right? The 10 can go all the way out there, and I go, I'll deal with the 10 at the end. I don't have to carry the stupid 10 around the whole time. Just remember that trick in a minute, because wait till you see the last example of the day. It's like really, really hard looking and giving it away. Okay, just relax. All right. Now what? He said switching colors.
Always something to do with the conjugate.
The conjugate, yes. Multiply top and bottom by the conjugate, which is the exact same radicals, the exact same pieces as the numerator in this case. But just if it's negative, I do positive. If it's a positive, I do negative. And if you're still not impressed by, I'm going to go through it one more time here. If you're still not impressed by the awesomeness of the conjugate, I'm going to show it off again. I'm going to move everybody around here. Now I'm regretting not making this smaller. Going to write a little smaller over here. This is a little bigger than I expected it to be. Limit as h approaches 0, one thing at a time with the conjugate. If you do it carefully and think about it, you'll understand the conjugate completely, what it is and why we do it. First two things. Root a plus h times root a plus h in the numerator. That's just a plus h. If that's confusing at all, don't forget. Root 7 times root 7 is root 49, which is just 7. That's what roots are. When you multiply them by themselves, they disappear. Then, the outside terms, root a plus h times this root a, I get root a plus h times root a, and that at that moment you immediately text me, and you're like, Mr. Todd, your conjugate thing doesn't work. You said you were going to get rid of radicals with the conjugate. I didn't get rid of the radicals. I've got a radical here in the numerator. This isn't going to work out. I'm like, keep going. Negative root a times root a plus h. That's why we changed the signs of it. It's perfectly designed. Negative root a times root a plus h. In fact, some people get so good at this, they just leave those middle terms out. They're like, those go. And then the last term is negative a. You multiply out the conjugates with each other, but you don't multiply out things that aren't conjugates. That's not going to achieve anything. That's just going to make a big mess. So in the denominator, in this case, I don't multiply it out because it's perfectly good the way it is. In fact, now that you've seen a few of them, that h sticking out is like, that's good. Let's leave that h out there. I'm going to need that. That's a key component to this. That's got to go with the numerator. Keep the 10 up front. Oh, it's easy to forget when you've got a common factor out there. It's easy not to carry it along. Yeah, so once you put it out there, you got to keep it. Lots of great stuff happens in the numerator. I hope you can see it. I'm just going to jump ahead. And there's the cancellation I was hoping for. Now, lots of times when you cancel, you don't, you just cancel it out. It's gone. And that makes you think, oh, it's cancellation. It's a bad word. It's not really cancellation. It's division. H divided by h is 1. But usually we don't need that 1. But if there's nothing left up there, it's a 1. It's still a 1. And so I get 10 limit as h approaches 0. 1 over, now the numerator, still a mess. Now I can sub in h equals 0. My last line is instantaneous rate of change equals 10 times 1 over root a plus root a. Instantaneous rate of change equals 10 over 2 root a. Ooh, I can do a little bit better. Instantaneous rate of change equals 5 over root a. 5 over root a. Should I rationalize the denominator? Well, I probably should, but I'm going to sub in anyways. It's not going to be my final answer anyway, so I guess I don't really care about that. But I pause for questions before I do my A speech. Before I do a speech. Okay. Why, in general, why is carrying the A around worth the tough algebra? There's two answers. Both are right. Max?
Because you can just sub in any number now. That is A.
Yeah, if they said A is 4, okay, and then part B says, well, try A is 9. You'd be like, oh, no. And you'd have to do it all again with 9. And then the next question is, okay, in the previous question, if A is 7, and you're like, oh, no, here we go again, and you do the whole thing. If you just carry the A, you can sub in any number. There's almost a better reason why carrying the A around is so good. Awkward pause. Trevor. If you give the instantaneous rate of change, you're not phased at all. You're like, no problem. Just imagine a homework question now where it's like, okay, find the instantaneous rate of change, like this one, at 100. And you go through all the way through with 100, and you get your answer, 5 over root 100. We're going to do that in just a second. And then part B is like, okay, find out when the rate of change is 4. And you're like, oh, no. Now I got to redo the whole thing with A's. Yeah? Whereas if you got the A's there, you're home free, right? Again, I ran out of space here. I got too arrogant. There, you see me get arrogant at the start? Oh, there's lots of space, I said. You don't care. You got paper. You don't even care about this. All right, so anyways, just give me a second here. I can fix this. That one. Insert blank page after current. There we go. Now I'm good. Now back to this page. Doot doot. What was I up to now? Instantaneous range of change is 5 root a. So then I'm saying at a equals, what was it? 100? IROC equals 5 over, I already forget. Was it root a? 5 over root a? 5 over root a, yeah. Over root 100. Root 100 is just 10. Yeah, what? You know, if you wrote 1/2, I think on this test I'd mark it right, and you're like, 1/2. Yeah, I know 1/2. It's right, but really what we're talking about is the cost of calculators. You know, so a good final statement is, therefore, the cost of calculators is changing at 50 cents per calculator. Why does this happen when you're in manufacturing? Building the first calculator, let's say we decided to make our own calculator company. Building the first calculator off the line is probably going to cost us $150,000. We've got to build a building. We've got to buy all the supplies. We've got to hire all the people. That first calculator is valuable. But once we've built the first one, the second one's going to be pretty easy. Whoop, just spin it off the line. And as things go along, it gets less and less expensive to build these things. This is why so many stores are selling things that you cannot believe the price at. You know, you go to the dollar store and like, how do they even get this here for $1? It seems impossible. The factory's all built, the machinery's all in place, the system to ship it's all ready to rock and roll. The truck shows up with $1 million store items at the back of the store. You know, once it's in place, it gets pretty inexpensive. Now, I don't know if it gets down to 50 cents per calculator. I don't know about that. But it gets, the next one costs less and less as you go along. Yeah. Questions there? That's big. Why is that so big? All right, that's fine. Woo, about that size. Okay, and then move these back over here for now, because they're going to be in the way for a little bit. A spherical balloon is inflated by an electrical pump. This is how I blow up beach balls in my backyard. I've got a pump. Plug it in, constant amount of air going in. Determine the rate of change of volume with respect to radius when the radius measures exactly 6. As you're blowing up a balloon, I don't know if you've ever noticed this. I certainly have noticed it when I have to blow up crazy stuff in the backyard for my kids. The first little while, the thing grows like crazy, and then it starts to slow down. And it's harder and harder to get that much bigger because it takes a lot of air to get it any bigger than it is. You need a whole shell of air around this thing. Just imagine if I had a balloon the size of this classroom and I wanted to make it 1 centimeter bigger on the outside. Just imagine the amount of air it would take to do that. That doesn't make sense. Think about the Earth. Think if you wanted to blow enough air in the Earth to make it 1 centimeter big or on the outside. You need 1 centimeter of air all around the surface of the Earth. So balloons really slow down as you go along here. None of that really matters for the question. Determine the rate of change of volume with respect to radius when the radius measures exactly 6. How do we know this is instantaneous rate of change? What is it about the question that tells us this is not an average rate of change question?
It says exactly.
Yeah, it's only giving us one particular x value here, or in this case, exactly one r value. So, you know what? I don't mind writing down m tangent equals limit as h approaches 0 of f at a plus h minus f at a over h. This is the last example today. Oh, I'm going to beat the break, no problem. Going to have a whole period of review or working on this homework, whatever you like. In the second half, I'll maybe write up a little test ideas thing for you. Yes? Okay, so m tangent. Okay, but I can do a little bit better here. I rock equals limit as h approaches 0 of volume at 6 plus h minus volume at 6 over h. I am going back to putting these 6 in there as I'm going back and forth here in the questions, trying to convince you about using the a value, but also showing you when in trouble, which we might be in a little bit of trouble here, once you see the formula for this, when in trouble, feel free to go back to the regular numbers here. What is the formula for volume of a sphere? Nobody knows. It's okay, I know, so it's going to be all right. But what has to be involved here if it's going to be volume?
3 dimensions?
3 dimensions, yeah. Whatever the formula's got, it's got to have 3 dimensions. And in this case, r cubed is in the formula. You know, but whenever you're talking volume, there better be 3 dimensions in there. So here's the volume formula. Four thirds pi r cubed. Here we go with cubes and 4/3 and pi's. This is going to get crazy out of hand. Well, yeah, maybe, sort of. Parts of it are bad. Parts of it aren't so bad. So 6 plus h into the formula. 4/3 pi times 6 plus h cubed. And then I'm going to do the other one in the other color there. Minus 4/3 pi times 6 cubed. Oh my, I'm going to say something panicky here. And hopefully somebody can bail me out right now and say, whoa, 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 it's not as bad as you think. I'm going to have to take 6 plus h and multiply that out 3 times. 6 plus h, 6 plus h, 6 plus h. Multiply that all out. Then multiply them all by 4/3 pi. Multiply this by 4/3 pi. Collect up all the like terms with all these 4/3 pi's and hope, pray, that I don't make a mistake in all there so this all works out. Does anyone see a different plan? That doesn't make this question perfect, but it can improve the situation dramatically. Unbelievable move here.
Oh, wait.
Heather, what do you see? Oh, it's good. Yeah, that's when you order the pizza in this question. You're like, you're panicking, like 4/3 pi and 6. There's cubes in here. What a mess. And then you just go, oh, wait a minute. Wait. 4/3 pi can just go out there. And the numerator is now, I'm going to write it out right now. 6 plus h, 6 plus h, 6 plus h. Minus 6 cubed.
Could we use the sum of cubes here to skip one step or no?
Difference of cubes?
Yeah, my bad.
Yes. Yes, it would be unbelievably good. Yeah. The first bracket would be 6 plus h minus h. You get, 6 plus h minus 6. You get h in the first brackets. Yeah, for sure you could. The reason I'm not going to do it is because difference of cubes doesn't always pop up to help you. And so I want you to see the full expansion, okay? I'm going to cruise along and do a bunch of algebra. Then you let me know after you see the algebra what questions you have, okay? Because life is actually a lot better than it was a second ago. Yeah? Like now it's just one triple expansion. I know the triple expansions are rough, but compared to what I was up against a moment ago, this isn't too bad. 4/3 pi. I think I can get one more line down there. As long as my knee holds up here. Oops. I pause for questions. Questions about those steps of algebra? Yes, the cubic expansions are nasty, but they're extremely repetitive. Once you've done a couple of them, you're like, okay, cubic expansion. It's a pain, takes me a bunch of lines, but it's not too bad. Did the miracle happen? Yeah, it did. The 2/16 went. That's definitely what I needed to happen, so that I have only h's left. And this time, I won't show the common factoring. Sort of giving you permission to, when you get to this moment, you can do this. That is just divide the h into all the individual pieces. When it's a simple situation like that, you don't need the common factoring there. I mean, you did do the common factoring and canceled, but it's just sort of skipping a step there. And then so when I put in h equals 0, that's when I can get rid of the limit. And you don't even need this whole step either. Subbing in 0 just makes all the h terms disappear, and I get 4/3 pi times 108. And let's see, 108 divided by 3 is 36 times 4 is 144 pi. And did they give me some units to use here? Centimeters. 144 pi centimeters cubed per centimeter. And that's instantaneous rate of change. It's a weird unit, centimeters cubed per centimeter, but if you think about it, it's not so bad. Every time the radius changes by 1 centimeter, you get another 144 pi centimeters cubed. So it's how many centimeters cubed am I getting per centimeter of radius. So units like that are weird looking when you first see them, but if you really think about it, maybe they're not so bad. What questions do you have there?
Centimeters cubed would be written as centimeters squared.
Yeah, maybe. And I'm going to address this a little more soon, is that if you're talking about a sphere growing, and when we're saying centimeters cubed per centimeter, really it's that we're adding on surface areas around the outside. I don't know, there's a kid on Max's hockey team when he was a kid who every day, with the tape he peeled off his things, he just added to the outside. He was adding area to the outside, increasing the volume. And that's what this is saying here. But we don't usually do it because this is much more descriptive. Centimeters cubed per centimeter describes exactly what's happening here, even though it's really centimeters squared we're talking about. It's a good question. Other questions?